Hi, I'm going to go over problem number 8 from your chapter 6 review. So you're given the graph of f, and it says let f be the continuous function defined on the closed interval from -4 to 3, whose graph consisting of 3 line segments and a semicircle centered at the origin is given above. Let g be the function given by g of x is equal to the integral from 1 to x of f of t dt. Part A is asking find the value of g of 2 and g of -2. So what's going on is g of 2, what you're going to do is you're going to plug in 2 for x. So if g of x equals the integral from 1 to x of f of t dt, and instead of x we're plugging in a 2, I have g of 2 is equal to the integral from 1 to 2 of f of t dt. And you're given the graph, so what you're really doing is you're calculating the area from 1 to 2, which is this little triangle here. Now the point is 2, -1/2. So this point here is 2, -1/2. The reason I know that is because my line goes from point 1, 0 to 3, -1. That means we went down 1 to the right 2. So that's a slope of 1/2. We went down 1 to the right 2. Therefore, this line has a slope of 1/2. So this point is 2, -1/2. So what we have here is base times height divided by 2, or 1/2 base times height. The base is 1, and the height is -1/2, making that -1/4. And that's your answer. And now we're doing the same thing for g of -2. So g of -2 would be the integral from 1 to -2. However, we can't go from 1 to -2. So we want to write from 1 to -2 of f of t dt. However, don't write that. What you need to do is you need to flip the integral. The bottom limit should always be smaller than the upper limit. So the -2 should be at the bottom, the 1 on top. So when we do that, now it's the negative of it according to one of our properties. So now g of -2 is equal to negative the integral from -2 to 1 of f of t dt. Okay, so what I did is, instead of integrating from 1 to -2, I flipped that integral, so it's now the integral from -1 to 2, but now it's the negative of it. And so now we just calculate the area from -2 to 1. So all we're doing is we're integrating from -2 to 1, which is this triangle, and this semicircle here. Okay, so what we have is the negative of, and so it's just, this triangle is 3/2 plus, and then the semicircle should have an area of -π/2. And so what we do here is just pretty much it's 3 minus pi over 2. But once we distribute that negative, instead of it being 3 minus pi over 2, it's now pi minus 3 over 2. That should be the answer. Alright, so for part B, now it's asking for each of g prime of negative 3 and g double prime of negative 3, find the value or state that it does not exist. So what we have to do is we have to take this one step further and differentiate both sides. So g prime of x, now what we're doing is we're using the other fundamental theorem of calculus, and we're taking g prime of x, and if we differentiate the integral from 1 to x of f of t dt, we have f of x. So g prime of x equals f of x. That's what we're using. So to calculate g prime of negative 3, well, g prime of negative 3 is just 2. Again, I know that because this line has a slope of down 2 to the left 2. So it's a slope of 1. So what we have is we have a point of negative 3 comma 2. Now we have to calculate g double prime of negative 3. Now if we differentiate g prime of x equals f of x, we pretty much now have g double prime of x equals f prime of x. And what we do here is, what we're looking at is pretty much f prime of negative 3. So g double prime of negative 3 is equivalent to f prime of negative 3. So what's the slope at negative 3? Remember, the derivative f prime is asking for the slope, and I actually just told you guys that it's down 2 to the right 2. So this, over the entire line here, we have a slope of 1. So those are your two answers for part B. For part C, it says find the x-coordinates of each point at which the graph of g has a horizontal tangent line. For each of these points, determine whether g has a relative minimum, relative maximum, or neither a minimum nor a maximum at that point. Justify your answer. So if we're looking for relative maximum, relative minimum, you should be thinking of critical numbers. So critical numbers is when the derivative, in this case, since we're looking at the graph of g, when the derivative of g, so when g prime of x equals 0, but according to this, g prime of x is equal to f of x. So it's the same as asking when is f of x equal to 0. So we're going to look at the graph, and we're going to see that we have zeros here, and we have a 0 there. Now, notice that the graph, this is all positive. So, when the graph of f is positive, that means g prime is positive. And then, at negative 1, we're down on the negative. So, what happened, now down here, g prime is negative. So, what happened, it changed from positive to negative. So what you got to ask yourself, is that a relative maximum or a relative minimum? Well, that's a relative maximum. So g has a relative max when x equals -1 because g prime of x changes from positive to negative. Alright, so now for the next one, so that takes care of x equals negative 1. Now at x equals positive 1, we notice that f is equal to 0 there, so we have a 0 there, which is the comparison of g prime being 0. However, notice that the graph of f stayed negative. That means that g prime stayed negative. So g prime did not change signs, therefore it's neither. G has neither a relative max or a relative min at x equals 1 because g prime did not change signs. And that takes care of part C. Okay, and now for part D, we're looking for points of inflections. So we're looking at g double prime. So we're now looking at g double prime of x is equal to f prime of x. So those are possible points. We're looking for possible points of inflection. So we're looking for g double prime of x equals f prime of x equals 0. Alright, so more importantly, to find the point of inflection, we want to see where, let me go ahead and erase this, where the second derivative changes sign. So where it changes from positive to negative or from negative to positive, well, that's the comparison of f prime changing. So the slope for f changing signs from positive to negative or negative to positive. So we see that f is positive, and then at x equals negative 2, it changes to negative. So we have a point of inflection at x equals negative 2. And there's your explanation. G has a point of inflection when x equals negative 2, since f prime changes from negative to positive. And this is good by stating f prime changes from positive to negative, so long as you include that g double prime of x equals f prime of x. Okay, so after x equals negative 2, we have a slope that's negative throughout, and then the slope of f changes again when x equals 0, and it changes from negative to positive. So we have another point of inflection there. So g has a point of inflection when x equals 0, since f prime changes from negative to positive. And by the way, I just caught a mistake on my first explanation. My first explanation should be a change from positive to negative, not negative to positive. And then finally we have a point of inflection when x equals 1, because that changes, the slope of f changes from positive to negative when x equals 1. So g has a point of inflection when x equals 1, since f prime changes from positive to negative. So what I've highlighted are pretty much your answers. So hopefully this video helps.